In this video, we're going to talk about continuous probability functions. Now, this is in the chapter devoted to talking about continuous random variables. So you might remember in the last chapter, we talked about a random variable, and a random variable describes the outcomes of a statistical experiment in words. So we would look at what would happen when we'd run an experiment like, how many heads would you obtain when you flip the coin 6 times? And the possibilities would be from 0 to 6. Now, in that particular chapter, all of our random variables were discrete, and discrete meant that it was countable. But we're going to talk about continuous, and continuous means that we can have decimals. So we're going to have to look at this in a little bit of a different way. So we're going to talk about how to find probability and kind of go through the theory of that. And then we'll look at a few examples and kind of move from there. And into the next chapter, we'll actually use some more solid techniques for finding the probabilities. So this is kind of preparing us for where we're heading. So first thing, the graph of a continuous probability distribution is a curve. And we'll look at some examples of that in just a second. But what's interesting about this is that the area under the curve represents the probability. Okay. So if we're talking about an experiment with probability and the area under the curve represents the probability, there's some interesting facts that we should know. First, the outcomes are measured and not counted. So because we are looking at continuous data, decimals, we are doing measurements, not counting. Okay. The entire area under the curve and above the x-axis is equal to 1. And the reason is, if this is supposed to represent probability, then it's supposed to represent all probabilities or 100% of all possibilities. So it equals 1 when you talk about it as a number rather than a percent. Okay, probability is found for intervals of values rather than individual x values. So right below here is an example. Finding the probability as x is going between C and D is the probability that the random variable x is in the interval between the values of C and D. That's how we say that. If x happens to equal C, we cannot find that. That's going to be 0. So it can't actually equal a number when we're talking about continuous probability distribution. So that's a big difference between what we're looking at in this chapter and what we looked at in the last chapter. We won't be able to find a set number. We have to be looking at intervals of number, ranges of number. It could also be something like x is less than a value, less than D. Okay, that is acceptable too. And then the next is that the probability that x takes on, this is just a commentary, is 0. And that's simply because we can't have area being represented as a single line. And I'll draw that in just a second so you kind of understand what that means. And then to say that the probability that C is less than X is less than D is the same as the probability that C is less than or equal to X and less than or equal to D is because the probability is equal to area. So there's no distinction between these statements here. They're exactly the same statement when we're talking about continuous. And it's because the probability is represented as an area. Again, we'll draw this out in a second. I want to show you some possible curves that we can see. These are the big 4 that we'll be looking at. The first curve, this rectangle, is kind of the most boring of all. It's called the uniform distribution. And as it kind of looks, it's a very simple distribution. Everything kind of has an equal chance of occurring. The next curve, we've seen this before, this kind of basic shape. It's a bell-shaped, but we're actually going to give it a different name as we're approaching it in this section. We're going to call it the normal curve. The normal curve. And we've seen these two kind of lopsided curves. This one would be a left skewed curve because the data is possibly having outliers on the left. And then over here, this last one would be the right skewed curve because we possibly have outliers on the right. Okay, so let's kind of do some examples of what this could kind of look like. Consider this function, and they're using function notations. They're kind of referring back to our knowledge of algebra. F of x equals 1 over 20. Now, ignoring the fact for a second that this is talking about a fraction, whenever we say a function just equals a number like that, that ends up looking like a horizontal line. So if I were to draw this function, so this would be, let's just say this is 1 over 20, that's that value. Then this function would look just like this. And it's going to stop. So it's basically going to look like the uniform curve that we saw above. It's going to stop. And they told us it's going to stop at 20. Well, that makes sense. The reason it makes sense is this area is supposed to represent 1. The total area is supposed to represent 1. That was one of the properties that we listed above. So the answer to this question, the probability between 0 and 20 is going to be 1. That's representing the entire area, all of the possibilities. And just so we're kind of driving this point home, 1 over 20, this is measuring this length right there, that length of a rectangle. And over here, 20 is measuring the length of this side of the rectangle. And I know that the area of a rectangle is length times width. So if length in this case is 20, we usually call the longer one the length, and the width is 1 over 20, well, 20 times 1 over 20 is 1. Boom, there you go. So it actually visually works out to be literally an area of 1. But all probability curves like this are going to assume to have an area of 1. Okay, so let's look at the next question. Using the same f of x as the previous example, construct a figure representing that f of x and this area from 5 to 12, and then they want us to find the area. So I'm going to draw this picture again. So this goes up to 1 over 20, and this goes out to 20. And it's going to be the rectangle. But this time they want me to go from the areas from 5 to 12. So here, let me kind of do that. So this would be 10, and that would be 5, and that would be 15, right? So 12 would be closer to 10 than it is to 15. So it'd be like here to here. So I'm going to go ahead and say that that's 12. So this represents the area or the probability between the values 5 and 12 for this probability experiment. Now they want us to find this actual area. Well, we kind of talked about how you do area of a rectangle, right? You multiply length times width. So in this case, the height is still 1 over 20 because it's still this height based on how tall the rectangle is. But down here, this would be 7 because the difference between 5 and 12 is 7. So 1 over 20 times 7, well, if we did this, we would just put this over 1 and multiply straight across. So 7 over 20 would be the probability that this is going to occur. And then we could divide and put it into decimal form. Excuse me. So as a decimal, it would be 0.35, or there's a 35% chance the probability is going to be between 5 and 12, or that this experiment is going to fall between the values of 5 and 12. Okay, so let's look at another example. Same figure, but this time they're giving us some decimals. Trying to make it exciting. So still 1 over 20, all the way out to 20. This basic rectangle shape. Okay, so to go from 2.3 to 7.5. All right, well, if that's 10 and that's 5, 2.3 is going to kind of be halfway between. So I'll just say that's 2.3. And 7.5 is definitely halfway between 5 and 10. There we go. 7.5. Okay, so there's this area. Now, let's actually find the area. So I'm going to go back to rectangles again. The height is still always, in every single one of these particular examples, when we're using the same f of x, the height is 1 over 20 every single time. So it's still 1 over 20. But this time I'm going to subtract 2.3 and 7.5. So that's going to give me 5.2. And 5.2, if I times it by 20, I can kind of use the same, I'm sorry, 1 over 20. I can kind of use the same idea where I put it over 1, and I'm doing really 5.2 divided by 20. And it wouldn't make sense to leave it in that form. So I'm actually going to go ahead and take a second and divide that. So I'm getting 0.26. So that would be the probability that this value, this random variable, is going to be between 2.3 and 7.5.